So last class we started looking at the advantages and disadvantages of the direct conversion receiver. So let's quickly review that. So the direct conversion receiver is pretty simple. You have a band pass filter to select your the band of interest. You have an LNA which normally operates throughout the band of interest, so you don't do any channel selection right up front. So you process the complete band, then you go through an IQ mixer. So in other words, it's a mixer with one side getting cosine, the other side getting sine, to separate out the two channels, the I and Q channels. And then you do some filtering and amplification and so on, and maybe the A to D conversion. Okay? And as far as the architecture goes, pretty straightforward, right? You only need two components really. You need an LNA and you need the single sideband mixer. That is, you need the IQ mixer to actually separate out the I and Q channels. Okay? Apart from that, everything else can be done on a case-by-case basis. And it is very easy to separate out now that the two channels are separated out, you can either extract the amplitude, the phase, the I and Q components, whatever you want. Okay? And we also said that if theta is not 0, that is the incoming signal is at some random phase with respect to your LO signal, what happens is your received signal at the two channels is a function of theta. Okay? So now obviously whatever constellation you have, your received constellation is actually slightly or a lot, right? We don't know what theta is, but it could be rotated, but that is very easy to take care of. You need to send some pilot symbols to actually extract out these this constant phase shift, and you can take care of this very easily. And obviously this has a lot of advantages. Starting off with its extreme simplicity. Okay, there is no image problem. That is a real, actually, when you start working with heterodyne receivers, you'll find out how difficult the image problem is, right? So really the direct conversion receiver is very nice from that point of view. You do not need any filtering from the point of view of the image, because the image is the signal itself. And because you don't need any extra stuff, right? You don't need to go off chip. You don't need to drive any of these filters. You don't need any of these on-chip filters. This is highly integrable. Small number of components, very simple components, and no bulky filters. And obviously you only need one single PLL, because you now have only a single conversion directly from RF to baseband. So from all these points of view, the direct conversion receiver is very straightforward. Now there were a couple of points that needed to be ironed out. The biggest points were the 1/f noise and the DC offset. Okay, both of these affect you in a very similar way, because you are taking the signal directly to baseband and you don't have a lot of components in your receiver. What happens is the signal does not experience a lot of gain. Okay, you may have maybe 20 dB, 30 dB of gain, not much more. And for your smallest possible signal, which may be just of the order of microvolts, you are really not giving enough gain to take care of these DC offset problems and these flicker noise problems. So to take care of either the DC offset or the flicker noise, there are some standard ways. And for example, as far as flicker noise is concerned, the biggest thing you can do is probably use very large devices, right? That will help you combat flicker noise. Larger devices will tend to have lower flicker noise. The larger devices will also give you better DC offsets because of better matching. Apart from this, you can also try to take care of these DC offset problems by using some kind of DC offset correction. As you know, most of these modern receivers have very heavy digital processing backend, very strong DSP processor to go with it. Even if you need to do this regularly, even if you need to keep doing this DC offset correction routinely every few milliseconds, that is very straightforward. Okay. Obviously there were other problems. LO pulling was a problem. and even order distortions. Even order distortion is actually a big problem, right? We have not considered it in a lot of detail, but in a normal receiver, in a heterodyne receiver, the IIP3, the third order distortion, was a big problem. In the case of a direct conversion receiver, the second order distortion was very important. How do you take care of second order distortion? First of all, have differential circuits. Anything else? You might need to do something extra, because differential circuits, differential symmetry again depends on matching between the two differential paths. You may not get better than 30 or 40 dB of matching between the two sides. So there are specific architectures to actually give you high IIP2. And you can read the particular section in Razavi to go over this particular problem. Okay? For example, he has a section devoted to high IIP2 mixers. Okay? So you can go through that to get more information. So that is as far as direct conversion receivers go. The other kind of receiver is the heterodyne receiver. So let's look at that. So what does a heterodyne receiver look like? So you have your antenna, and the first thing you have is your band select filter. Then of course you need your LNA. What next? What goes after the LNA? Image reject filter, because before you go through the first round of mixing, you now need to have an image reject filter. We'll call it the IRF. So this is omega RF, and you have omega LO going into the mixer. After this, what do you have? Why do you need another filter? Yeah, you probably need several things. First of all, you may want to reject the omega 1 plus omega 2 component from the filter. So that is one thing you need to reject. The second thing is you might actually want to have some amount of channel selection right here. Okay? You might want to have some amount of channel selection. So in other words, you may not want to so remember that the actual channel selection may or may not be done in the baseband. Okay, you can choose to do it in the analog also. Nothing prevents you from doing that. But I'll just say some filtering. Some filter here. Maybe some programmable gain. And after this, now I'll go through my usual IQ mixing. And maybe my low pass filter and so on. This is my IQ output. Okay. So obviously the first thing you see is that there are a lot of components. First of all, gain is not a problem with this heterodyne system. Okay, because you have several stages of, you have some RF gain, you have some IF gain, and you can have some baseband gain if you want. Okay, so the gain is very well distributed. What about the filtering? Filtering is also very well distributed. You have some amount of band select filtering up front, under the LNA. Then you have the image reject filter. Then after the first round of mixing, you have one set of filtering, and so on. So filtering is also very well distributed. In fact, one of the reasons this became very popular is because you can do everything in stages. You have gain very well distributed, you have filtering very well distributed. So really many of the trade-offs are much easier than what you would have. So you need the IRF for the image. So these are the important things. Second thing is, because you have so much gain upfront, you don't have any DC problems. Okay. How do you choose your IF in this case? So remember that this is omega IF. How do you choose your IF frequency, the intermediate frequency? Correct. So you have two cases. So you can choose either IF very large or very small. Now depending on that, the trade-offs are different. So let's say you choose high IF. Okay. If you choose high IF, this means that your image reject filter becomes very easy. Okay, because your IRF is a band pass filter. If you choose a wide IF, filtering out your images becomes much easier. Okay. However, the minute you do that, your channel select filtering and this portion, the minute IF is very large, now this portion of the circuit just became more difficult, because you are trying to get the same amount of gain at higher frequencies. Okay, you are trying to get the same filter, the adjacent filter you are getting after this first round of mixing now needs to operate at higher frequencies. Okay, so the subsequent filtering just became difficult. IF stage design. Is more difficult. If you choose low IF, obviously it's exactly the other way around. You have easy IF design, but your IRF becomes very difficult. Okay, you need higher Qs. So that is automatically a trade-off between channel selection and image rejection. So selectivity and so trade-off between image rejection will define the sensitivity, because if you have a larger image coming down on top of your signal, your sensitivity gets affected. Okay, so this is a straightforward trade-off, right? So the choice of IF will completely depend on whether you can how easily you can design your IF circuit, and how much of the how easy it is to design your image reject filter, whether you want to put it off chip or on chip and so on. Okay, so now obviously designing your image reject filter is not straightforward. Okay, especially if you want to choose a low enough IF, designing your image reject filter is not at all straightforward, and in most cases people would go in for an off-chip filter. However, we know that CMOS is not well suited to drive 50 ohms. You do not want to have off-chip components, so you actually need to come up with some architectural level solutions apart from circuit level solutions to actually target the filter itself. People have come up with architectural level solutions to actually combat this problem. Yes, but any loss that the filter has will directly add to your noise figure. Of course you can, right? But normally you do not want to do put anything, as much as possible the LNA should be the first component, right? You have already put in a band select filter because you don't want to have out of band interferers. If you need to put in one more filter, that makes it all the more tougher. I'll call this section image reject receivers. And the motivation for this is that the IRF is off chip, bulky, 50 ohm interface, okay. Obviously this will have an impact on noise, power consumption and so on, and linearity. So we need to come up with an architectural level solution to take care of this image problem. So what do we know about the image? First of all, we know that if your desired signal is here, okay, and this is your LO, your image lies exactly at IF on the other side from the LO. So I'll call this the omega IM, which is the image. So you know that if this is omega IF, this is also omega IF. So what you want to do is you want to come up with an architecture or with a receiver which will treat the RF signal, desired RF signal and the image signal differently. So it needs to process these two signals in a different manner. That is what you fundamentally want. Okay? Okay?
The Q of the bandwidth filter is high, that can't be overcome the image problem.
Yeah, but how do you make sure that the Q of the band select filter is very high?
We will design that. The design of the bandwidth filter is.
Yeah, so who's going to design that? No, yeah, but I'm asking who's going to design that? Again, the idea is to relax your trade-off, not to make the design of one circuit very easy. Of course, I can say that I can design a very strong, if I can design a very high Q filter, I don't even need to design the band select filter to be high Q. I can just design a high Q image reject filter, right? So the idea is to make things easier, because things are not very high quality in CMOS. Filters are not, you cannot get very high Q filters, right? You cannot get, traditionally you couldn't get a lot of amplification, but I'll say you can't get nowadays the devices are fast enough such that you can get a lot of amplification with, with less amount of power. But really the thing to note is that compared to the amount of noise you are adding, right, especially in terms of down the stream at baseband, flicker noise is still a big problem. Flicker noise and DC offsets are still huge problems with in CMOS design if you compare it with bipolar design, for example. Okay, so see, the idea is no. Apart from that, the band select filter offers a very specific function. Okay, it is getting you your the band you are interested in and nothing else, right? The image reject filter, on the other hand, is a custom circuit, because the band select filter may be a standard band select filter for every. If I have a let us say a wireless LAN receiver at 2.4 gigahertz, the band select filter will always be from 2.4 to 2.4835, right? It's a very specific filter. The image reject filter, on the other hand, is a custom design. One receiver may actually choose an IF of 50 megahertz, another receiver may choose an IF of 20 megahertz, and so on. You can't really put these two together and say I'm going to design one single receiver, right? The purposes of these two are different, and therefore these are two separate components. That is the way I would look at it. Okay?
Instead of putting image reject filter off chip, we can't put band select filter off chip.
Band select filter is already off chip. That's what I'm trying to say. Band select filter is already off chip, okay, and you're okay with that, because you definitely need to get rid of your out of band interferers, because your interferers could be anywhere, all the way to maybe 15 gigahertz. Okay, you really don't know, because there is so many systems out there. and so you definitely need something to kill out whatever is out of band. But for that purpose, you would much rather have a general purpose filter rather than a very specific filter. Okay, so the coming back to the image reject receiver, you are going to rely on an architecture which will process the desired RF signal and the image signal differently. Okay, now before we look at what kind of circuit does this, let us look at the kinds of circuits that can actually give you a shift by 90 operation. Okay, so let us say I want a circuit which does a shifting by 90 degrees. So I have a desired signal, I want to shift it by 90 degrees. So for example, I have x of t sin omega t. I want to make this into minus cos omega t to shift it by 90 degrees, right? And have you people heard of the Hilbert transform, right? What is the Hilbert transform? Huh? Yeah, it's basically a Hilbert transform provides a 90 degree phase shift, right? So obviously we want to implement this Hilbert transform using some kind of circuit, right? So what kind of circuit can you think of that does this? Can you think of a circuit that will actually give you 90 degree phase shift? Okay, so he says if you know the frequency of operation, you can use some LC based circuit. So what kind of phase shift does an LC based circuit give you? So what kind of circuit will give you a 90 degree phase shift? Well, yeah, I mean your idea is correct. So the obviously the current through an inductor or the voltage current relationship through an inductor or through a capacitor has a 90 degree phase shift. So that is an interesting way to think about it. So apart from the 90 degree phase shift, we also don't want to disturb the original signal also, right? We don't want to disturb the amplitude of the signal, for example, right? So as it turns out, a simple circuit which does this. So let us say I take Vn. Now remember, as it turns out, what I really want for this is I not only want the 90 degree phase shifted of the version of the signal, but I want the original signal itself also. Okay, because I'm going to use this 90 degree phase shift to actually differentiate between these image and the RF signal. Okay, so to do this, I actually need to preserve both the original signal as well as the 90 degree phase shifted signal. So one of the things I'm going to do is on one side I'm going to have a CR circuit. On the other side I'm going to have an RC circuit. Okay, obviously these two capacitors are equal and these two resistors are equal. So I have two signals V1 and V2. So what I have done is, on one side, if you look at V1, the phase shift is pi by 2 minus tan inverse omega RC. Okay, On V2, the phase shift is just minus tan inverse omega RC. Okay. Now if I choose the RC values correctly, what can I get? I can get 45 degree phase shift on one side and minus 45 degree on the other side. Right? And I can get equal amplitudes on both sides. Remember, because the amplitude is related to the relative values of the impedances of R and omega C, the resistance and the capacitance, what I can do is, I can make sure I get plus 45 degrees and minus 45 degrees on either side, and I can also get equal amplitudes from both sides, V1 and V2. However, there is a caveat. The equal amplitude will happen at exactly one frequency. If you deviate a little bit from this frequency, the two amplitudes will not be exactly equal. Okay? So the amplitudes will be equal only at omega equals 1 by RC. If there is any deviation in this, the amplitudes will not be equal. The phase shift on the other hand will be 90 degrees for all frequencies. Okay? Obviously, as you can see, one of them is pi by 2 minus tan inverse omega RC, the other is minus tan inverse omega RC. Okay, so how do we use this to actually generate our image rejection? So as it turns out, the first kind of architecture which is going to do that is called the Hartley architecture. So let's say I have the signal plus the image going into this receiver. So what I'm going to do is, I'm going to mix the signal plus the image with the sine and cosine of the LO signal. Then I'm going to low pass filter the two outputs to get rid of the omega 1 plus omega 2, omega LO plus omega RF component. Then on one side, I'm going to apply a 90 degree phase shift. We are going to see what is going to happen to this kind of receiver. Okay? On one side, I'm applying a 90 degree phase shift. On the other side, there is no phase shift, and I'm going to add these two outputs. So let us name these points A, B, C, and D. Okay, we want to look at the signal at each of these points. So let us say the RF signal was XRF of T, was some narrowband signal ARF cos omega RFT, and the image signal was XIM of T, which was AIM cos omega IMT. So at A, okay, so at this point, I am going to get mixing of omega RF plus omega IM with sin omega LOT. So what I'll get is, I'll get ARF by 2 sin omega LO minus omega RFT plus AIM by 2 omega LO minus omega IM T. And I am going to rewrite this differently. I am going to write this as omega RF minus omega LO, and I am going to put in a negative sign here. Okay? So let me actually put that in blue. Okay? Similarly at B, XB of T will be nothing but ARF by 2 cos of omega LO minus omega RFT plus AIM by 2 cos of omega LO minus omega IM T. And XC of T is the 90 degree phase shifted version of XA of T. What is that? If I have a 90 degree phase shift on minus ARF by 2 sine omega RF minus omega LO, I'll get a cosine signal. So I'll get plus ARF by 2 cos of omega RF minus omega LOT minus AIM by 2 cos of omega LO minus omega IM T. Okay? I have just phase shifted the signal at A. Now for the signal at D, the signal at D is just the sum of the signal at B and C. What do I get? If you notice, these two signals get cancelled and these two signals are additive. So what I get at B is ARF cos of omega LO minus omega RF T. Okay? So in other words, this 90 degree phase shift has actually managed to distinguish between the RF signal and the image signal. Right? So the 90 degree phase shift between the RF and the image signal in terms of image and the polarity. Okay, because one happens to be on the lower side of LO, the other happens to be on the upper side of LO. So it is able to distinguish between the polarity. Okay. So, and as we know, in practice, instead of applying 0 and 90 degrees, we can also do minus 45 and plus 45. You will achieve exactly the same thing. That is what this circuit does. This circuit will actually give you minus 45 and plus 45 instead of 0 and 90. But that is okay. The circuit will behave exactly the same. Because you are interested in the relative phase between the RF and the image. Mm-hmm. But that is okay. Effectively, it is the same thing. Correct. You just split that into two parts. That is all. Okay. So now the problem is, actually, what is the problem with this? So this looks very good.
So the magnetic issue is also, the amplitude is also, you can only one frequency.
Correct. So that is one big drawback. Obviously, the fact that the amplitude is matched only for one single frequency is a huge drawback, because any signal will actually have a finite bandwidth, and you will get cancellation at an exact at one particular frequency, but around that frequency you will get imperfect cancellation, right? Okay, so that is one problem. Anything else?
You will also have the unit for omega L minus omega S and omega L omega L.
What was that again?
You also have to use omega L minus omega S. There are also used to consider the signal as a single phone.
Correct.
You have to 90-degree ratio to the phase signal. I mean, the image as well as the RF image. My point is,
Okay, fair enough. So the 90-degree will have to apply to omega RF and omega IM, which means this is applicable for low IF systems, right? Okay, fair enough. What else? If you do it using an RC filter, yes. There may be other cases where you may not be able to do this. In the case of the RC filter, that's right. You get a 90-degree phase difference irrespective of frequency. But for other phase shift mechanisms, this may not be true. Anything else? Okay, so apart from this, you are trying to match a capacitance and a resistance together in the two paths. If there is any mismatch between the filters on either side, whether it's this kind of RC filter or whether it's something else, right? The first two things are systematic problems, right? Amplitude matching is a systematic problem. Even if everything is perfectly matched, the two capacitances are exactly equal, two resistors are exactly equal, the amplitude matching happens only at one frequency. Whereas the two capacitors themselves may not be identical, the two resistors may not be identical, and therefore you could have mismatches between the two sides that will again affect your image rejection. Okay? And in that case, we now need to actually define something called the image rejection ratio, because we need to figure out how much of the image is actually getting cancelled. Even if you have, let us say, if you're considering very narrow band frequencies, you need to figure out how much of your signal is actually getting, how much of your image is getting cancelled. Ideally, it may be 0 dB. Ideally it may be perfect cancellation. You may get 0 of the image signal at the output. But in reality, you will always have some residual depending on the matching. Okay? So, to do this, you will actually have to assume that there is some amplitude and phase mismatch between the two parts. So what I'll do is I will not go through the math. You can actually put in, so for example, you can assume that LO inputs are mismatched. You can combine all the amplitude and phase mismatches on either side and draw them into the LO. So that is one easy way to do it. So you can assume that on one side you have ALO sin omega LOT. On the other side you have some ALO plus epsilon cos omega LOT plus theta, right? And derive the amplitude and phase mismatches with respect to epsilon and theta. So what we are going to do is we are going to define two important things. One is called the image to signal ratio. Okay? What is the image to signal ratio? Of course, the image power to the signal power at any point. At some port or at some node in the circuit. Okay? And once we define this, we can also define what is the image rejection ratio of the system, of the receiver, because at the input itself, the two powers may not be equal. We have not said anything about the image power with respect to the desired signal power, and therefore you may already have a power ratio at the input. You want to find out how much lower that has become at the output. So we are going to define image rejection ratio as the image to signal ratio at the input, at the output, over the image to signal ratio at the input. Okay, so this is the image rejection ratio of the receiver. So in other words, let us say at the input the image was 10 dB higher than the desired RF signal. At the output the image was 40 dB lower than the desired signal. Then the image reject ratio of the receiver is 50 dB, right? So you can define it with respect to the powers at the input and the output. And again, you can, for a receiver, you can decide it with respect to the amplitude and phase mismatch between the two paths. I'll leave that up to you can go ahead and read the textbook for that. Razavi has a pretty good explanation of the image rejection ratio, so you can take a look at that. But the primary thing to remember is that it depends on both the amplitude and the phase, okay, between the two paths. Now let us go back to your Hartley architecture. Primarily, what are we doing here? We are taking these two signals, we are applying a 90-degree phase shift to one side, we are not doing anything to the other side. Now obviously this kind of architecture is, there seems to be some kind of mismatch inherent to the way we are hooking up the circuit. Because on one side we are not doing anything, on the other side you are applying a 90-degree phase shift. Something like this is definitely going to have mismatch. Okay? So as it turns out, there is actually an easier way to do this phase shifting, and there is actually an easier way to apply this phase shifting such that it's more symmetric with respect to either side. So the second type of architecture is called the Weaver architecture. You have a question? The way we have implemented it, you mean here? Yeah.
How we are implementing it, the top part goes to this VR.
Correct. That is true. Yeah. If you implement it this way, this resistor capacitor, we have actually done plus 45, minus 45. There is lesser chance for mismatch between the two sides. Perfect. Okay. So the other way of doing this distinguishing between the desired RF signal and the image signal is using what is called a Weaver architecture. So instead of applying a phase shift to the signal, or rather you can apply a phase shift to the signal indirectly. Instead of adding an explicit phase shifter, you can actually apply the same phase shift through a mixing operation. So the Weaver architecture looks like this. So you take your RF input, so you go through one round of mixing, okay. So the first round of mixing, you mix with sin omega 1t and cos omega 1t. Now instead of actually adding a phase shift, okay, you can do a second round of mixing. Now the way you actually achieve the phase shift is, instead of mixing it with the same frequency, you again mix with the sine and cosine components. So obviously what you have done is, instead of adding the phase shift in the RF path, you have actually pushed the phase shift into the yellow port of the mixer. Okay, that is all you have done. Okay, so again let me name these nodes A, B, C, D and E. Okay, you can again write down the signals at A, B, C, D and E. You will find that again this receiver also distinguishes between the RF and the image, and it gives you a negative sign with respect to the image, and therefore the one difference is that you just need a subtraction operation, not an additional operation here. But you will again find that at the output the image gets cancelled, whereas the RF signal does not. But more importantly, because you are using mixing operation instead of some kind of phase shift operation, this can be more broadband compared to the original scheme. Obviously the amplitude and phase mismatches will still exist. If you have phase mismatch between the sin omega 1t, sin omega 2t and cos omega 2t, again you could have a image rejection problem. Similarly, if you have gain mismatches between these two mixers, you could again have a gain mismatch problem, and therefore an imperfect cancellation of the image at the output.